Okay, so good evening once again, everyone. I trust we are all good and I'll be able to speak so well. Okay, so welcome to ML Lagos technical session for me. So there are a couple of ground rules. So um, please be respectful to everyone's session. When sorry, when you have questions, raise your hands. Keep your as a speaker is going to be presenting. Everyone has to stay muted, and if you want to ask questions or draw the speaker attention to something, you kindly raise your hands so as to maintain otherness. Uh, when we are to ask questions, we speak on one at a time, which means like you have to raise your hands, and the speaker is going to like the speaker or myself will call out your name to ask a question. Um, so yeah, so keep discussion focused on machine learning, AI, and topic on agenda, and rest of the ground rule. So let's please follow the rules. So yeah, so we are going to go straight to avoid any delay. So after the speaker does presentation, if you have any questions, raise your hand and speaker is going to answer to them. So once again, welcome to technical session for me. And we're going to be talking on embedding model and why they matter in brag and everything. So a little intro about a speaker. Please kindly pardon my pronunciation. So Chuku Ibuka is a Okeke, is a machine learning and applied AI engineer, passionate about building intelligent systems. He also specializes in natural language processing. And I would like to open the floor for Ibuka to take the stage. So, on to you.
Okay, good day. Good evening, everyone. Am I audible enough? Can you see me fine? Can you? Okay. Thank you. So, script is KK. I'll be talking on. I'm the speaker for this technical session. Where I'll talk about the importance of embeddings in RAG for LLM products. So, let me begin by sharing my screen. Please, during this session, I'm let's say this is my first time doing this. So that's it. Let's just proceed. Yeah, so yeah, so this is what I'm going to present and talk about. So, when we are working with LLMs, machine learning AI, the concept of embeddings are like very important. So let me just begin. What comes to your mind when you hear the word embeddings? Can anyone just like type it in the chat box? The chat box. Uh, Specific. Okay, someone said insertion. Yeah, you might be correct in a way, but not 100% correct. So let's just say embeddings helps the our computers to try and understand the concept of whatever like we are trying to request or message decided. Just so, let me just use an example. Just know that embeddings are graphical presentations of real world data and they help to preserve semantic relationships. Just forget this technical jargon where I say such a virtual distance and vector space. But if you're into machine traditional machine, you have come across this. So let me just use an best is kind of an example I try to compare the mathematical concepts of longitude and latitude to embeddings. So let's just say, the way we present the distance of Earth, we use latitude and the longitude coordinates. So we already know that any place on our planet can be represented by these two numbers. Now, embeddings work on the same principle, but instead of mapping physical locations, they map semantic meaning. So an example of an embedding model is the bi-directional model. So what Ben does that takes any sentence, regardless of their length or complexity, and then puts it into seven state numbers. Now this seven state numbers is kind of the embedding Gemini. So when what Ben does that the transformation helps to preserve semantic relationship. There's sentences with similar meanings. So this just like a quick example. So this document, when you say the sentence, it cuts out on the math, it can become a vector with exactly similar state numbers. Well, for example, in traditional machine learning, when you're working with, let's say you want to do sentiment analysis, you will notice that for you to be able to predict if the text is positive or negative, the way you train, you use some algorithms like TF-IDF algorithm, and it kind of takes your text, the text data, and converts it to a vector, which can be fed to a machine learning algorithm model. For example, in that case, we have a SG boost model, or I say a random forest model. So TF-IDF, count vectorizer, those were like the early stage of research done when trying to get convert text data into vectors, which can be used for machine learning process. Is there any noise in the background? Yeah, just give me a minute. Let me confirm if I'm on this noise cancellation, please. Okay, can you hear me clearly now? Someone said it is cracking. Hello? Yeah.
Okay, sorry. I think there is like someone is speaking at the background, so it's kind of like distracting.
Okay. So let me move to. So is it better now? I'm in next page. Is it better now? Yeah. Can someone see the five, please? Okay, thank you. So let me just move. So I just have a question. Yeah. Just saying this, how would you create like a system that can recognize that cats out animals and a feline rested on the floor have similar meanings without using embeddings? So are you going to like use a rule based? Are you going to work with a rule based approach, or what other approach do you think would be used for that? Can someone just like give a solution, or should I move on to the next? Okay. Okay, let me be so here's what I think. I said looking at this mathematical example, where I say the sentence that the task in the past can become a vector, and the sentence that the parent resting on the work can get a different but mathematically similar vector. So the mathematical distance between these vectors reflects their semantic similarity. So I was trying to ask now, can you create a system that can recognize that the cat sat on the mat and a feline rested on the box have similar meanings without using embeddings? Like you're not you want to identify patterns in your image. Okay, did you get the question? Okay, sorry, this is the question. This is the question. I said, how will you create a system that can automatically recognize that the cat sat on the mat? Okay, 10 frequency. 10 frequency could work. 10 frequency could work, okay, correct. But it might not be efficient when compared to the current state of the art embedding models that we have currently. I will just move on to the next. So now, why embeddings solve fundamental AI problems? Now, there's a semantic gap that is involved with traditional computing. So, before embeddings, computers faced the challenge that some researchers called semantic gap. That means computers can only process text through exact character matching. And this approach is not the same way that it's not the same way that it doesn't work the same way humans understand language through meaning and context. So you see, for this example now, if you search for, if you put in a query called cappuccino in your computer, it can maybe only find documents that contains that exact word. It might miss other documents such as espresso, drink, Italian coffee, or coffee beverage. But now, with the concept of embedding and similarity context, and if you type in cappuccino now, it can recommend similar concepts which falls in as Italian coffee, espresso drink, and the rest. So in this case now, embedding tries to solve the semantic gap that traditional computing had. Okay, we can so just sorry that I just tried to make it out by asking some questions. So can anyone like share a recent experience? Let's say when you wanted to search for something but you couldn't find it because you didn't use the exact keywords kind of. Okay, no one. Please, if you can hear me audibly, like can you just signify please? Okay, yeah, some reason. Okay, apologies for the noise and this background. Yeah, more about fight. Okay, okay, that's okay. Okay, so now let's moving on to the next stage of the multimodal revolution. So initially when chat came out, you have noticed it couldn't like accept image data effectively, but due to advancement in research. Yo, I'm using my laptop to present companion mode and I'm using my phone to talk. That's it. For it means for each month that asked. So that's just yeah, that's it. So looking at this now, okay, okay, let me see. Sorry, which one is isn't it? Okay. Alright. Yeah, it's on mute now. So due to research, researchers were able to work on how embedding models could work beyond just text data as integrating image data, audio data, and video data. So these days now, if you like upload an image or any AI LLM, DeepSeek, Gemini, or ChatGPT, it could be able to like understand the context of that. And so this helps. So the true revolution of embedding lies not just in improving individual tasks, but in creating unified semantic understanding across all forms of human expression. That's just the and so I think some researchers in machine learning would have come across this concept called multimodality. Well, I specialize really in text data, that is natural language processing. So moving on to the next. Well, these are about the embedding quality revolution. So there has been some progress in improving embedding models. Just for example, when BERT came out, in the average benchmark, which is used to evaluate embedding models, this was the performance of BERT on that benchmark. And then Google embedding models, the recent one that came out this year, around I think February, March. This is its performance on the benchmark. So you can see that there have been like a good number of improvements in just 7 years. So let's just what does this benchmark does? So what with this benchmark you can the benchmark is used to evaluate embedding models across diverse tasks. There's question answering. There's when you ask them AI question and give you response, fact verification, citation prediction, document retrieval, where which can also fall under the concept of RAG. So you can see stacks from this. So what are the real world impacts of this improvement in embedding models? So such systems that could understand users' intent rather than just matching words has really helped in LLM products. And then question answering systems that wouldn't be hallucinating but are factual and could help in finding relevant information. And we also have recommendation engines. So just putting it here. So just for another example that in 2018, embedding based search system could just correctly identify relevant documents for 2 out of 10 queries. But today's system can identify relevant documents for 8 out of 10 queries. So this improvement transforms embedding based search from an interesting research project into a practical replacement for traditional search systems. Okay. Does anyone have any questions so far? Apologies for the background noise. Okay, no question. So I'll be talking on the evolution of text embeddings. So earlier during my presentation, I said something about TF-IDF and count vectorizing and how they kind of work when if you're working on a sentiment analysis traditional machine learning project. So the part model embedding represents decades of progress done by researchers to capture meaning mathematically. So the first generation is our bag of words approach. So in the bag of words approach, we have this TF-IDF, 10 frequency, it falls under that. Then we have the latent semantic analysis. So in this case, researchers try to use mathematical matrix optimization to see if they could discover hidden relationships between words and documents. And then we have LTA. It's was another approach that was used to model documents and mixture of topics. Currently, there's something that has been trending for a while, which is called mixture of experts in machine learning research. Just moving on. What's the main limitation of this first generation in text embeddings was that most times they ignored word order and context. So in this case, yeah, let's say the sentence and the cat sat on the mouse and the mouse sat on the cat would be presented identically, despite the fact that we know that the cat sat on the mouse has a different meaning from the mouse sat on the cat. So that is just like the first generation of text embedding. Moving on to the second generation, where we had neural code embeddings. So the concept of neural code embeddings was actually based on the hypothesis that you shall know a word by the company it keeps. I don't know if you have gone through this concept where someone says that king minus one plus one is equals to three. So that concept was based on this second generation of text embedding, like the neural model. And you have what to take, very hard to implement steep ground, and then try and see if you can predict the target word from surrounding context itself. Yeah, so this was just breakthrough. So for the first time, it's master operations on one vector reflected semantic relationships. And then in this now, there was still a limitation for the second generation text embeddings. So in this case now, each word had only one representation regardless of their context. So the word bank may have the same embedding, and that bank might refer to okay, a financial institution on the side of the river. So there were limitations to this second generation of text embedding model. So I just have a question. Can please I just like want this to be started. So if you think about the word bank, I deposit money at the bank versus I start in the river bank. Should this have the same mathematical representation? There are two options, A or B. You can respond by typing in the message box. Thank you. Okay, someone said no, they shouldn't. Yeah, they shouldn't because I deposit money at the bank has a completely different meaning to I start on the river bank. Yeah, yeah, you're correct. They have different contexts, so you're correct. So moving on to the third generation of text embedding models, where we have contextualized embeddings. So first thing first, well, some researchers told that if we do sequence to sequence and then we do there's this LSTM that we were good in natural language processing until the good guys at Google decided to help us, and then they built the transformer architecture. So transformer architecture has helped in machine learning, AI, and AI and LLM. So even your GPT 52, 53, and the rest, they were all built from transformers. So just moving on, BERT, which is the bidirectional encoder presentation of transformer. So previous models in when it comes to embeddings, they read the text from left to right or right to left. But with BERT now, it's to process text bidirectional. So following the its bidirectional encoder, and you can see the entire context simultaneously. So that means this enabled a good understanding of what's meaning in context. So how BERT works is that it has a max language model training where it tries to hide words and learn to predict them from the surrounding context. Then a next sentence prediction, where it learns relationship between sentence and larger text structures. And then a bidirectional processing. So you can use both left and right context to understand each word. So another part of this third generation where we are talking about contextualized embeddings is model development. There's T5, there's PAN, and then current Gemini and GPT-4. So what the major difference between this third generation and previous generation of text embedding model was that this third generation could be able to understand meaning behind words and try to recognize irony and metaphor and maintain a good coherent understanding across long documents. And if you notice, they perform better than just using TF-IDF or can't vectorizing or just what to vec. So currently, most LLM products they are using this third generation of text embedding models. So, moving on next. So next, I'm talking about document embeddings and withdrawal encoder architecture. So you know that we all know that I believe we all know that what embeddings can capture individual 10 meanings. So that means many word applications require a complete understanding of documents, paragraphs, or text passages. So now, document embeddings helps to solve this challenge by creating a single vector presentation that captures the overall meaning and context of entire text, enabling comparison and rest. So just this is a challenge. Consider that you're working on presenting a 50-page research paper as a single 768 dimensional vector, and you want to preserve its essential meaning, key concepts, methodological approach, and the rest. Now, this compression must maintain enough semantic information to enable accurate retrieval when someone satisfies the concept. Even if there's different terminology that than what is in that original paper. So now, moving on, the concept of dual encoder helps in retrieval. So here is this now. When we are working on queries and documents, you should know one thing you should know that let's say for example, if you upload a document from ChatGPT, your query, your queries, that is your request to ChatGPT might be kind of different in a way, different from the time document you uploaded in a way. So with dual encoder, you are trying to have a query encoder that specializes in understanding the user's intent and information, that is the user's query, and then you have a document encoder that will try to represent the detailed context and comprehensive information that you uploaded. So, for example, it's just two encoders. So the single encoder uses the same neural network architecture for both queries and documents, and it assumes that they can process identically. So this approach might look simple to implement, yes, but it is not that effective. For example, if it's putting queries like best restaurant downtown, it might treat that query as the same as full restaurant reviews, which might miss fundamental difference in their structure and purpose. But with dual encoders, with dual encoder architecture, you can be able to separate the query encoder and the document encoder so that you want to mix in their context and the rest. So training through contrastive learning. Dual encoders learn through a sophisticated training process. It's called contrastive learning. So it's more like you're trying to train the encoders and the rest. So we did during through this process, it learns to create embeddings where semantically related queries and documents are positioned close to each other in mathematical space, while unrelated content is pushed apart. So just let's have an example, a question. Why do you think queries and documents might need different encoding strategies? Somebody reply. Okay, no response. Did anyone get the question? Okay, someone replied that documents have different semantic context from query. Yes, yes, you're correct. That that is one of the major reasons why queries and documents should have different encoding strategies. So moving on to modern document embedding approaches, there are a lot of approaches available, but the major ones currently are sentence-based model. So, so I say, for example, a legal document will have different context from how people query it. Yes, you're correct. So if you upload a legal PDF, someone might put in a query like, what was the court, the judge decision for based on the trial or the case in this PDF, and someone else might put in who were the plaintiffs and those kind of stuff. So yeah, documents should have documents have different semantic context from queries. So yes, you're correct. So moving on now to the modern document embedding approach. We have sentence beds. We have so what sentence bed does that it uses this single encoder. So if I see this Siamese, just know that I think about single encoder approach. So it uses single encoder approach and triplet network structures to learn meaningful sentence presentations. And then we have that one created by Google Defines Gecko. And then we have another one called Cobet. So Cobet uses multi-vector representations that store embeddings for individual tokens, enabling fine-grained matching. Does anyone have any questions so far? I move to the next slide. Okay. So next. So I'll talking on vector search algorithms. So embedding models are good. but if you're working in production, you need to make sure that you need it to scale. That is one important thing. You need to scale. So just like what I say, creating embeddings solves half of the challenge. So another challenge is making sure that embedding model is efficient through searching through millions or billions of vectors to find the most similar ones to your query vector. So what this means is that your query vector, just like I used the previous example, when you upload a legal PDF, someone's query vector might be who are the plaintiffs for this case. Now you need your embedding model to be able to go through, to be able to like search through, and that's where you have vector search algorithms, similarity search that will help out in this case. So let us say the main challenge lies in selection. This computational problem becomes difficult as the number of documents grow. So for this is just an example. The time required for linear search through 1 billion vectors, if searching 1 million vector takes 1 second, is 16.7 minutes. But modern approximate nearest neighbor algorithms complete the same search in milliseconds. So, has anyone heard about approximate nearest neighbor (ANN), which is a concept in traditional machine learning? So what ANN does that it's kind of implements a trade-off where it sacrifices small amount of accuracy for computational speed. And because of that, ANN could help in a vector search algorithm. So this so going to talk about this locality sensitive hashing where you organize by similarity. So what LSH does that it operates on a simple principle. Design hash functions so that similar items are more likely to hash in the same bucket. So instead of traditional hash functions, is ANN in any way related to KNN? Not really. It's not. I don't think so. It's related to KNN. So just talking about LSE today. So what LSE is? Here's an example. Think that let's say you want to organize a massive library where some similar topics are automatically shared near each other. And then let's say someone asks for a book about engineering and you need to search for artificial intelligence section rather than the entire library. So what LSE does is that it has multiple hash tables where it uses several different hash functions to increase the probability of finding similar items. Then it has a bucket-based search in that book with bucket-based search, can only start within those hash buckets that likely contain similar vectors, and then you have the tunable accuracy. So more hash table provide better recalls, but require more computation. So yeah, you have to decide: do you need more? You need like more computation cost issues or not? Then you have memory efficiency. So yeah, you store compact hash codes rather than full vectors. Yeah, another approach is the hierarchical navigable small words. This is a graph-based approach. So what this does is that it creates a multi-layer graph structure that mimics how you navigate the real world. So just as you use highways or you're using your local road, HNSW uses long range connections in upper layers and local connections in lower layers. So just let's say just imagine a transportation network where your top layer represents highways that connect major cities, and then your middle layer represents regional roads that connect towns, and then the bottom layer represents local streets. So if you want to travel anywhere, you know you have to start on the highway, then move to the smaller roads before you then reach your final destination. So what HNSW does that it has a multi-layer structure where the upper layers have fewer roads with longer connection, and your lower layers have more roads with local connections. And then another concept in HNSW is that it has a greedy search strategy. So at each layer, it moves towards the node that is most similar to the target until reaching a local minimum. Then progressive refinements, it moves to lower layers for increasingly precise search results. And HNS logging has like an excellent performance in the way that it achieves sublinear search time with high accuracy in practice. So another approach is SENN, and this scalable approximate nearest neighbors is a is an approach that Google researchers are currently working on, which they are proposing that it might be more better than what we currently have available. So what this Google's SCANN does is that it represents state of the art of production vector search, and it's kind of available in Vertex AI. Okay, let me just talk about Vertex AI. Vertex AI is a Google Cloud AI service. So if you're using Google, if you want to use Google AI services, you could access it through Vertex AI. So just what SNN does that it defines a vector space into vertical clusters using then partitioning strategies, and then it has a scoring phase and it has a rescoring phase. So this three-phase approach helps you to achieve superior speed and accuracy trade-offs compared to other algorithms. And Google believes that this is why it is needed in production systems that are to serve billions of queries. So I just have a question. Let's say you're working on a task. So which factor do you think is most will be the most critical? Do you think maximum speed, highest accuracy, memory efficiency, or balanced performance across all factors are important? Can anyone give a response? Okay, someone said, yeah, balanced performance across all sectors. Yeah, that is important to get a good and efficient results. So moving on to the next. Yes, also depending on the use case, depending on the use case. So if you are more factual, but at the place where I work at, let's say I work at an agency for big pharma. So when you're working with pharmaceutical data, medical data, you need accuracy. So most times you don't consider speed, you consider accuracy to be very important because if you don't have the accurate results, it could it could be bad for what you're working on and the medical field that you're working on. So next slide. So I'm going to talk about vector database. Now, vector database are kind of different for traditional database in a way that let's say the vector database it stores vectors and it is not that easy to use SQL queries on vector database like that. Let me just go in now. Now let's say I've already talked on the concept of vector search algorithms where it helps us solve similarity search. Now, you need a database. Real-world application needs systems that can handle complex users, maintain data consistency, provide backup and recovery, security policies, and scale horizontally. So you already know about traditional relational database, your SQL or NoSQL. So you already know that relational database uses ACID properties that helps to ensure transactional consistency and data integrity. But with vector database, it integrates similarity search that's that he uses HNSW and other algorithms. And then the query interface focus on the k-nearest neighbors with distance metrics. So now, what are the modern vector database solutions? So the vector database landscape is this purpose-built vector database and traditional database. So if you have been working on open source projects or if you have come across some open source AI LLM project, you would have heard something about ChromaDB, which is an open source vector database. You have heard about Qtrans, which is also another open source vector database, and then you have Pinecone, which is another open source. But personally, if you're not using AWS GenAI stack, there is AWS Bedrock. We suggest that you should just use Pinecone in working in production. But if you just want to build a MVP or proof of concept, you can start with ChromaDB or any other open source alternative. I'm not going to talk about them here. So latest AI vector search is Google's cloud service for vector database, and then you have Pinecone. So Pinecone is a vector database not open source, but it's really effective in production environments. They have Wikit. I didn't talk about it. So Wikit is also another open source vector database. It uses GraphQL APIs, and then it combines hybrid search with vector similarity. So, okay, yeah, PostgreSQL is a traditional database, but I think recently, I don't know, 2022 or 2022, they integrated PG Vector, which is like trying to integrate vector operations of vector database into PostgreSQL. So you could use that if you want, and then you also have Elasticsearch from on LinkedIn or X. So LLM engineers or AI engineers most likely argue that Elasticsearch is better than using Pinecode or Command. But your use case, it depends on your use case and what you want to work on. So just like I said there, the choice between specialized vector database and extended traditional database depends on your specific requirements. So if you know you're working on your vector workloads, it could benefit from specialized solutions that optimize entirely for similarity search. And this is where your Chroma DB, your vector database is your Chroma DB, Pinecone, or Qdrans will fall in. And then if you think that you want to work with vector database and traditional database, then you could then integrate Elasticsearch or PostgreSQL integrator. So there are some issues with deploying vector database in production most times, which is embedding duties. So when embedding models improve, sometimes you need to develop strategies for migrating existing vector collections in embedded space without disrupting production services. Or I think in this case, how it's done is that because let's say for example, just 2 weeks ago, we migrated our vector database from DB to Pinecone. That is was that we just did everything in our dev environment before, and we had to confirm everything works before we now mesh to our main environment. So that just for this embedding duties. The research architecture. Research architecture most production system combine vectors and search with traditional keyword filters. So let me talk about RAG. So we try on below, and the link of this slide will be shared to the community so you can just go through it. We are almost running out of time. It's almost 9 p.m. So I'm just going to talk about RAG and how RAG solves learning limitations. So and at the initial stage, large language models, their knowledge most times is frozen at training time. So there are some questions like before RAG concept was integrated in ChatGPT. There's a question if you ask it, like what's current information to tell you that my cutoff training time was this. So I do not know anything beyond that. This was like when 2022, 2022 when ChatGPT was launched. So what's with Frog now, we would have dynamic access to current information through retrieval from updated knowledge bases, grounded response, and coordinated source material with explicit citations and rest. So can anyone just share an experience where you asked an alien about recent events and what happened when you did that and how limiting was it? Okay, wow. Just move on. So I'm going to just okay, someone say it was sports score. Okay, maybe you're trying to figure out Chelsea against Real Betis. What was the current score? And yeah, this has seems better because they integrated RAB in their chatbots, ChatGPT chatbot, and then they integrated web search. So that's why the search feels better. But unlike early 2022, when you wanted to like get updated information through ChatGPT. So just moving on, let's talk about Harvard solve LLM implementation. LLM imitation, sorry. So it implements a two-phase architecture that separates knowledge storage and maintenance from language generation. So that means the reason why this separation is important is that it helps organizations to keep knowledge current without retraining models, right? providing language models with relevant context. So here's the first stage, the offline knowledge indexing phase. So this phase processes your organization knowledge into a suitable format that can provide relevant context for future queries. So that's where you hear something like ingestion phase, where you have to ingest your document. So if you're hot with this framework, launching or Lama index, you have come with across the concept of ingesting documents and then chunking. But recently, some developers tried to not implement chunking because Gemini, Google say they are provided us with a 1 million context window. So some developers don't use chunking. Like I don't use chunking again if I'm working with Gemini API, but I'm not working Gemini API, I implement chunking. And then we have the embedding generation and vector storage. So vector storage is that your embeddings, the generated embeddings are now stored. Index embedding in database are optimized for similarity search with metadata for filtering and routing. So when it comes to filtering metadata, Llama Index has the metadata query that you can use to filter. Then we have the real-time phase that responds to user queries by retrieving relevant knowledge and branch. Yeah. So this is chunking strategy that could be used. So critical design decisions. So when you're trying to decide in a RAG implementation, you have to ask yourself, are you working on, you need to consider chunk size optimization because a larger chunk can provide more context, but it could reduce semantic focus. And then smaller chunks where it might lose important relationships. And then you have to look into retrieval count selection, the ranking strategies, and the rest. So these just advanced RAG techniques and motivator approaches beyond basic craft. But I think we end on this. Does anyone have any question? Almost done. Time is almost up. You could speak. If someone with your hand, yeah, you could talk to ask a question. Mr. Steve. Hello. Can you ask a question? Raise your hand.
Okay. Can you hear me?
Yeah, yeah. I can hear you. Audible.
Okay. You mentioned a couple of algorithms for doing similarity search. So I was going to ask how which of like how resource intensive are each of them? Like let's say I have limited let's say I'm using what's it called Postgres and PG Vector. So I'm running things on my own like VPS. So, how can I decide which to use based on the limited like RAM and what's it called CPU and this thing I have? So how do you decide which to use to do similarity search?
Okay, based on your question, you're using PG Vector. Apologies, I've not worked with PG Vector, so I don't actually know how it works in Postgres. But if you are to focus on computational challenge of similarity search, I believe you should not start with one of the algorithms that won't consume a lot of memory in a way. To start with locality sensitive hashing, to start with this and just try to organize by similarity. And then along the way, you could just progress. Do you get that?
Yeah, thank you. I see.
Okay. Okay. Does anyone else have any question? Hello. Any questions, please?
Sorry, stay. Have you asked a question? Answer.
So, Mr. Stay, do you have any other questions?
No, no, I asked my question already.
Okay, that's okay. Does anyone else have any questions? Just have like 4 minutes left.
Okay. Um, Sebuka, like, are you done with your presentation?
Not really done, but I'll share this to the community for anyone to go through it. And if anyone have any questions, they could reach out to the community or reach out to me.
Oh, thank you. So, the slide will be made available to everyone, so you can go through at a later time and do practicals on it. So, in absence of any question, um, thank you guys once again for attending the technical session. Make sure you don't. Okay, so you the slide will be shared to everyone by mail, so you can just be on the lookout. Mail will be sent and it contains recording of this session as well as slide, so you can go through it. All right, so please don't forget to follow us on Twitter at ML in Lagos and on LinkedIn Machine Learning Lagos. So we have an upcoming event, which is the grad series. I'm sure all of us have seen email. So please go through the mail and register. It's happening next month. More details will be sent to the group chat. And if you have not joined the group chat, please kindly join the group chat to stay informed for community events and information. So we'll be having a June office hour and June talking session. More information will be shared on the group chat. So please make sure that if you are on group, you're in community group chat if you aren't. So yeah, we also like your feedback. So this will be shared to the group. So you can fill the form and give us your feedback on how the session went. I'm sharing it here so that you can like fill the form and it will still be shared to the community. So yeah. So thank you so much, everyone. Thank you so much, Mr. Yubka, for the wonderful session. It was really interesting. And I'm sure like every other person can say the same as well. Um, thank you guys, and make sure you don't miss out on the June office hour grad series, which is going to be very interesting, and as well as the June technical session. So have a wonderful. Oh yeah, so you can, for those that haven't joined the group yet, I would let me drop the link here so you can join. Sorry, give me a minute. Let me get the link here for you so you can join our community. So you can stay informed of our latest events. coming. I'm sorry, give me a minute. Trying to get through things. Hmm. Okay, yes, okay. Okay, well, mhm. Um,
Yeah.
coming.
I'm okay.
Okay, yes, thank you so much, Neil. So the link is on the chat, so you can click on it and join the community. Thank you, thank you. Yeah, so please, for those that haven't joined the community yet, please join the community so you can get constant information of all the events that is going to be happening in our community. So many events, things learn a lot. So yeah, so thank you guys once again for joining the session, and um I wish you a wonderful evening and wonderful night rest. Bye guys. Thank you.